This webcast talks about quantified energy conservation diagrams. So we've learned now how to calculate the various types of mechanical energies, gravitational potential energy, elastic potential energy, kinetic energy, and dissipated energy. And so now when we use conservation energy diagrams, we can use the calculated values of different energies to help solve for specific variables in the problems. The basic strategy is listed here. First, you make the energy conservation diagram the same way that you have done it for qualitative cases. Write the energy conservation equation. Okay, this is where you start doing something new. For each type of energy, for example, gravitational or kinetic or elastic potential or dissipated, you're going to plug in the snapshot formula for how to calculate that type of energy. And then you're going to solve for the desired variable. So I just want to emphasize that in our conservation equation, we may write delta EK equals delta EL or something like that as our conservation equation. But every time we want to calculate the values of these energies, we use these snapshot formulas because we are finding the amount of kinetic energy at position A or the amount of elastic potential energy at position B. We are looking at specific instances in time at position A and position B, and we want to find the energy that it had at that moment. And so always use these snapshot formulas. Let's look at an example to illustrate how this works. This is actually problem 8 from worksheet 8E. And so this problem says that we have an 8-kilogram cart moving at 5 meters per second, and it collides with a spring constant of 50 newtons per meters. So it will make the spring compress, and then and so we're going to look at it at position B, where the cart is motionless. It is not moving because the spring is compressed. It is getting ready to reverse directions, and the spring force will cause the cart to move back in the other direction. But when we look at it at position B, it's not moving. So therefore, at position A, when we first look at the cart, it is moving at 5 meters per second. It has not touched the spring yet, so the spring is at equilibrium. So the only type of energy in this system that has the cart, the spring, and the earth is kinetic energy. At the end, at position B, when we look at the system, the cart is not moving. This may just be for an instant, but at this instant it's not moving, so there is no more kinetic energy. And the spring is compressed, so there's a lot of elastic potential energy. There was no mention of friction or anything like that. So that basically is the type of energy we have at A and at B. So our conservation equation is that the change in kinetic energy equals the change in elastic potential energy. The total energy of the system did not change, but the way that the energy was stored did change. It was initially stored as kinetic energy, and at the end it's stored as elastic potential energy. So the question is, how much was the spring compressed? So to answer that, I'm going to start with that energy conservation equation. And then I'm going to substitute in the snapshot equation to calculate each type of energy. So the snapshot equation for kinetic energy is 1/2 mass times v squared. the snapshot equation for elastic potential energy is 1/2 k times delta x squared. Now I'm going to plug in the values of everything that I know, and there's one thing here that I don't know. That's the delta x of the spring, so that must be the thing that I'm solving for. And as I plug in, I want to make sure that all of these quantities are in standard units. So for example, mass has to be in kilograms. Velocity has to be in meters per second. The K, the spring constant, has to be in newtons per meter. Okay, and in this problem they all were in standard units. I didn't need to convert anything. So I plug in my mass and velocity and K and solve for the delta x, and I find that the displacement of the spring was 2 meters.